Hello and welcome back. In today's session, we are going to talk about one of the basic system design use case that's called URL shortening. Right? So the URL shortening is one of the basic system design where when we think of system design, this is one of the basic use case we can think of. It's not easy to use those URLs because there's billions of trillions of links available in the internet. So before going more into the topic, if you haven't done it, please subscribe the channel and click the bell icon to get notified. So when we are talking about the URL shortening, again I'm saying so URL shortening is one of the basic use case, right? So here we can really go through different components and how we can really orchestrate the whole system when we are designing this URL shortening. So in our internet, there are trillions of resources, trillions of websites available in the internet. So if you think of that, the URL to access those resources, those websites are really super long. So in that case, we can't able to share those links or share those URLs through any social media or any messaging service or something like that, because every service has their own limitations. Like sharing any URL, sharing those as a text to other user. So in the text field there is a limit, right? If you think about the Twitter, so Twitter, whenever you are writing some text, they have some specific number of characters you can only share in a message, right? So if you have a long text, so they will divide into multiple parts, right? So in that case, if you are going to paste one and going to share one big long URL, and then the recipient is not getting the full URL at the same time, right? So hope you understood the basic of the URL sorting use case, why we really need. And most of this is very simple but very effective, and it's being used most of the services because every service is on the internet, right? So that's how so what would be the different requirements we could have? Right. So if you think of the functional requirements, a functional requirement would be like first, it should be able to generate a short URL, and the second one is it's easy to copy and share, as we share like the Twitter use case, and it should able to user can pick a custom URL as well. So what if system will give you a URL rather than I need my own URL. So you might have already seen those kind of things in different services or environments. So mostly, for example, YouTube, right? So in your YouTube, whenever you are really creating any channel, so you are unique ID, right? But you can always create an alias for that particular for your channel, and you can provide your own text, right? So that will be your own URL. So that's whatever the URL available behind the scene, but whatever you have provided the URL, that will be your URL. You can share that with others, right? So and next is one of the feature is link expiration. So whenever we are creating any short URLs, so that URLs should have some expiration time, right? Otherwise it will, if one user really creating one URL for one time sharing and we use for some time, and if that will keep holding in the system for longer time, then there is no use, right? That's not necessary actually. So to make the system robust, probably one of the feature, it should be the link expiration time. And another thing is like configurable expiration time. So whenever we are providing expiration time, that should not be a constant for all. That should be configurable, because whenever you are building any service, so in that service, so it's not necessarily it's for open world, right? It might be leverage for the enterprise system as well. So when it comes to that, so every enterprise user might have a different requirement for the configuration side of the house, right? So, and if you think about the operational requirement, what would be that is like highly available. The service we are building should be highly available, or the system we are building should be highly available, and there should be very minimum latency, that low latency we are saying, and it should be easy to maintain. Okay, think about how we can build a system for that, right? In the first place, what are the things comes to our mind, like what could be the system to design for this, right? So if you think of that, in the first place, the picture in our mind it comes is, okay, there will be some user, okay, and they will access some service available somewhere. That service we are going to call maybe some URL sorting, okay, and that service will take care of the sorting the URL from a long URL to short URL. So all the algorithm will be available here, right? And then what this service will do, send that particular short URL with a long URL to the any some database system, right? Some database system, and then that once that pair of key value will be stored in the database, then it will send that particular value back to the service, and that service will take care of responding to that user. So that's how it is, right? And this is what it comes at the first place comes into the mind, correct? And then so if this is what the case, it's completely abstracted now. The service, when we are thinking of this service, the URL shortening service itself, right? So it might be available in a single server, right? One server maybe, and this database server also may be available in one server, right? So there might be one user, right? So this is one of the high-level design we could think, right? So if you think of like this works if this is one user, like two user, maybe work for the 100 users, right? So what about if we think of scaling it up, right? So when these services are being built, it's not for 100 people or 1,000 people, right? It will be definitely available for millions and billions of users, right? And also it's not for one URL or two URL or 100 URL, right? It might be it definitely used for millions of URLs to be short, right? So that is the case. Then if that is the case, then we have to think of the scaling. To scale the system, we have to think of other different factors into consideration when we are really scaling any service, right? So to make a scalable or make a system available for bigger and larger audiences, then probably we have to take other factors into consideration, right? So what are the other factors? Let's talk about one by one, like what the service and what kind of algorithm we can really use for that to build the service, and then we come to the estimation, and then we come to the what kind of different features as component we can use to leverage all these features, like load balancing and the latency, low latency, and the storage spaces, and how can we transmit the data, and the data access, right? How we can access the data easily. To build the service, URL shortening service, what we can do. So there are multiple ways we can build the service to shorten URL. So what are the different algorithms we can really use to shorten URL, right? So first and foremost, we can think of like, okay, we can use some cryptographic technique or algorithm to make it happen. So MD5, one of the way encrypt the whole URL and make it shorten by applying the algorithm 62. Why it's called base 62? So whenever we are trying to shorten any URL, right? So in that case, it needs some characters available for a short URL we are creating out of a long URL, right? So in that case, we might consider of cap A2G, right? Let's say cap A2G and small letter A2G and maybe the digit 0 to 9, right? So that is nothing but this is 26 characters, this is 26 characters, and these are 10 digits characters, right? So in all total, if we just add it, so it all about 62 characters. So that's why we used to call it the base 62, right? That's 62 characters. So if we take this algorithm into consideration, how many number of unique URLs we are going to get, right? Because for every long URL we are trying to shorten it, it has to be unique, right? So how many number of short URLs we are going to have? So that's one of the case we have to think of, right? So in that case, let's, for example, if it's a company and maybe organization, they might think of maybe max to max it will go maybe some multi-billions of URLs. Then maybe that would be the case. You can go with, okay, so you can go with some five letter characters, right? So length should be five with combination of five letter and digits, right? So if that is the case, then it will be 62 to the power 5. Okay, so how many URLs you might get? You might get somewhere around if you think of like, okay, we increase it a little bit and we make it, instead of length 5, if we can make it length 7, then what it will be somewhere around 62. So 62 to the power 7, it will be somewhere around maybe 3,500 trillion. Okay, it's trillion. So that's how trillion unique URLs, right? Unique URL. So then how many years this service can be solved, right? Because every time we are sending any URL, so it should, that URL has to be shortened with a unique URL that has to be 7 character length. And this is a service we are going to build, and we are going to apply the algorithm, sorting algorithm, the base 62, right, with the 7 character length. The sort URL has to be 7 character of length, and we are going to use the base 62 mechanism. So we are building the service. So now we have to estimate, like, if this is the case, what are the number of total traffic it has to be, how many users, how many URLs it's going to come to the system. That's the one we need to really think. So before going to this estimation, so I would really encourage to go through one of my previous video available in the channel, so that talks about more fundamental thing of the estimation. How can we plan and estimate any system we are trying to design, and what are the different capacity it will really need to for any system we are going to design. Definitely when we are talking about estimation, it's estimation, right? So it's not an actual number what we are going to predict, but it's somewhere around that. We are just predicting that some estimation, so that accordingly we can plan for our system in the future, or next 5 years, or maybe for next 10 years, right? Okay, let's talk about the traffic, right? For the traffic, we can think of like, okay, so assume like for the traffic, assume like there are the ratio of read and write, right? Read and write is 100:1. That means while or you can say 1:100 or something like that, right? So that means like if there are one short URL generated, right? Then there are 100 users, 100 reads onto that particular URL shorter. That means that we can say 100:1, right? That's read for URL, right? Read for short URL, maybe. Correct. So in that case, we'll think of like if per day there are 1 million URLs coming per day, then what will be the number of URLs we are going to get in per second for that particular service, right? So that will be somewhere around 1 million divided by this is 86,400 seconds, right? So this is the number we have in total number of seconds available in a day, right? So in this case, when we're saying like we can really calculate how much number of total requests coming to the system, coming to the service to shorten it, that means it will be somewhere around 10 to the power 10 to the power 6, right, and divided by 8400, right. So that will be somewhere around 10,000, yeah, 10 to the power 6 minus 2 divided by 864. You know what I did, right? So that will be 10 to the power 4 divided by 864, and that will come around how many? 12 URLs per second. So see, when we are thinking of 1 million, it's a heavy, right? And how the service can be scaled. But when we really come down to a very specific per second, so it's very, very, the number we are getting is very reasonable, right? So in this case, so all these things we have already explained in the previous video when we talk about the capacity planning and estimation, right? So this is what the number of URLs we need to really shorten every second. So that has to be the functionality of this service we are going to we're going to build, right? So if you think of like one ratio, read and write ratio, so when we are writing one, there are hundreds of users are reading that particular URL. So that's what we are really thinking of. I mean, estimating the traffic. So it has to be the traffic. So accordingly, we have to design our system. So then come to the storage, right? How much storage we need? We are going to store maybe things, right? Maybe the long URL, short URL, right? And maybe created on. Kind of why we are taking this creator on into consideration, because we have functional requirement, right? So that is called as expiration, right? If we will not keep this creation date in somewhere stored, then we can calculate that expiration date, right? So the expiration also we can, it has to be configurable. So you have to have one a field called expiration time, right? So maybe this expiration time would be considered as a date, or after how many days or something like that. So in that case, right, and we have to have a ID, so where we can map it who actually created that, right? So maybe the ID for this, right? Or ID might not require, because this ID itself is acts as a ID, it's unique for all, right? Don't require, right? And along with this, we might need a user information. So if you go to, there is a URL called tinyurl, right? So so in that website, you can generate a short URL out of a long URL without logging in, right? So for if you are going to make that whole service paid version, then probably there are some paid user will use that, or any user they want to leverage other features. Those features are available only once the user log into the system. Then in that case, we have to have the user details, right? So user details called maybe UID, right, and uname, and username, maybe user first name, user last name, and other any other reference you can add created on. Why you are putting it created on? Because there are some users, they have just logged into the system, but they never use any of this service, right? So in that case, so we can have in future, we might have a preference to delete these users from the store, right? Because those are just unwanted users, they just log in and just went away, right? So that's the case. So in all these things, how much storage space we need to store those data? So if you see, like storing the UID, maybe it's 32 character, and the first name will maximum allocate maybe 20 characters, and for the last name we might also allocate 20 characters, and the TSN date. So TSN date will be always it's a date format, right? Maybe it's 8 byte of data, right? So 8 bytes, right? bytes for storing the single user detail, right? So 10k users per day, right? 10k users per day, so we have to divide it 10k, right? Yeah, 10k 10 to the power 3 into 80 bytes, right? So for users, it will take 1 MB of storage space per day, right? Per day. So that means it's not necessarily like, I mean, every day that user will be used, right? So if for next, if you think like every day we are getting 10k users, then if you think of for next 10 years, so how many it will be? So it will be 1 MB into 30 days, for example, into 12 months. So 12 months into that will be the 10 years, right? So that's how it will be. It's 36 it's 36 360 60 MB, right? It will be what it will be for no. So 3600 MB. So that means the it will be somewhere around GB. Okay, if 3.6 GB. So the storage, it will be 3.6 GB for 10 years to storing the user information, right? So let's think of like, I mean, whatever we are going to calculate here. Let's, for instance, to store every URL information, it might take 500 bytes, right? 500 bytes. So for 500 bytes for every URL, so there are 1 million URLs, right? So URLs we are going to start per day. So that means it will need so if we are getting 5000 MB of data, we need to store the all URL related stuff into the storage every day. This is per day, right? Per day. Then how much it will really need for store the data for next 10 years, because when we are building any system, we have to have a plan to build the system for another 10 years and how it will perform, right? So when we are estimating that, then this is 5000 MB. It's nothing but like 5 GB, right? 5 GB of data in 4 day. So that means for next 10 years, how much it will be? 5 into 365 into 10, right? So 5 gigabyte per day, that has to multiply by 365 days for a year and another 10 years, right? So that will be somewhere around 50 into 365, right? So that's how it will be, right? So it will be somewhere around 1825 gigabyte. It's nothing but like 1.825 GB. It's approximately 2 terabyte, right? GB, it's TB, I would say TB, it's approximately 2 terabyte. So to store the data for next 10 years for user information, it will take 3.6 GB plus for the storage, right? 3.6 GB for the user, and the URL, it will be 2 terabyte, right? 2 terabyte. So it's approximately 2 terabyte only, right? 2 terabyte only. So for storage, we need 2 terabyte for all this information, right? So that's about the storage. And what about the data read and write latency, right? Data latency. So how can we read and write that? For memory, we see like that's 1:100, right? When we are writing 1, we are reading 100. That means, so if we think of like total memory for caching the data, so let's think of like 25% of the data we can store, we can really cache it, right? So if that is the case, then how much total data we have stored in the system? So that's around 2 terabyte, right? 2 terabyte. So if that is the storage is 2 terabyte, then 25% of the data we are going to, have in the system, right? In the cache memory. So that will be, it's not necessarily the 2 terabyte, right? Because for per day, somewhere around 5 GB, right? 5 GB of data per day. That means out of 5 GB, we can probably go with the 0.25, right? That will be somewhere around how much? 1.25 GB of memory space we need every day to 25% of the whole usage in the cache memory, right? So the cache memory we are holding is because of like it will be make the whole read faster, right? So and also whenever any new URL coming to the system and going to write it, then it can always find anything. I mean, it want to source from here as well. When we think of the scale, right? So the scale, when we think of the scale of this, right, total URL, total number of URL keys, and total number of read and write billions, multi-billions, and the storage we need is 20 terabyte or maybe up, and total memory you might need a 10 gig, right? But if you see here in this diagram, what are the problem statements over here? It could be, right? So the user is, I mean, one or many can be, right? So here the service we have deployed is maybe one server, right? So when it's acting in one server, so it is very difficult to really handle the whole 3.7 or 4, near about 4 billions of transactions, right? So in a single server. And the same wise, when it comes to DB, and DB it need to have 2 terabytes of storage space to store, and also need to have the number of requests need to be fetched frequently, read frequently, and write frequently as well, right? So one server cannot be really do all these things. I mean in low latency, correct? So first problem statement would be like single point of failure. Why? Because we are using only one server for our application. Because if that particular server goes down, then we don't have any way to use that service, correct? And if the database also available in one server, right? So if that database server also goes down, there is no way the service can, even if the service is up and running, there is no way, there is no DB available for that, and the service whole will be meaningless if it keeps running and it's not sending any response to the user. Rather it's responding like service not available kind of thing, right? So that case it will be a single point of failure. Okay, and the other problem is definitely the scaling. So it cannot handle this much amount of request or this much kind of storage space, all these things in this single server architecture, right? So and the other thing is like definitely the maintainability. Like anytime we saw like there are lots of spike in the usage, or lots of incoming request coming to the system, then we should have ability to scale it off, or if there is a cool off time, we should able to bring it down. So for those those things that are not available in this architecture part, right? So in this architecture we can add some more components into this system, so that the whole system can be scalable enough, right? So to get into those kind of systems, so when we'll think of like how can we really handle lots of billions of transactions to the system. Of course there is a way, right? So how can I do that? So you might have heard about load balancer, right? And if you haven't, then we already have one related video we have already published. Those are the most important for any system design to make a scalable system, right? So you can always go through that and take a look in the whole video. It will give a very clear idea like what are the components really need for any scalable system, or what are the features or drawbacks of those particular components, right? And how we can leverage those components into any system design, right? If you think of, there is a component called load balancer, right? So load balancer is one of the component that can be leveraged in any system design to balance the load coming to the system. Okay, so there are multiple phases available in any system. So for every phase we can incorporate the load balancer, right? So in this case we can add a load balancer in between the external user and the service itself. So we can integrate a load balancer here. Another load balancer we can always have, like once the number of total requests is hitting to the service itself is properly managed, then also there are a lot of load also hits to the database edge worth, right? So to do that, so we can also have one load balancer over here edge worth. We can add load balancer here, right? So that's one of the case, right? Adding load balancer to the system can really manage the load coming, billions of requests coming to the system, right? And definitely, definitely, whenever we are getting billions of trillions of requests to the system, so it's not easy to handle that. Okay, even if the load balancer is available in that case, but not necessarily it will be completely handled, right? That's why there are sometimes it comes to the rate limiter. It comes in the picture. So we are not going to talk about the rate limiter at this point. We'll talk about that in a different session altogether, right? But we are not really touching to this particular component at this point, right? So just keep aside with this. Even if we are adding one load balancer to the system, but still we have the problem still exists because of the single point of failure, because we have only one server available in the whole system, right, for the application and for the DB as well. So what we can do, we can replicate this particular service into multiple servers. We can add servers for the application, for that particular application, which takes care of shortening the URL. Right. So in that case, what it will happen is whenever any multi-billion request come into the system, right? So it will really pan out all those requests to different servers to process those. So all those servers can process the different requests parallelly, right? So you can always see the benefit of the parallelism, right? And the distributed system of the service can really process the request independently, right, and parallelly. So that's the performance we can really get benefit out there. So now the another point is like, okay, if we are configuring that independently, then there is also doesn't make sense, because if one is goes down, then others can really take care of that, those requests, right? And there are some mechanism available for the load balancer. You will always get, as I said, like you will always get the other previous video we have already uploaded related to the system design fixtures, right? So those algorithm, this load balancer can apply and send the request to fan out the request to different application servers, right? So now there is no single point of failure here, right? And the same probably capability we can also add to the database side of the house. So if we can just add more database servers to the system, then whenever this any request coming from multi-request coming from the application server to the database, then this load balancer is sitting here to fan out the service to a different database. So this is one of the design we can put in place to really replicating the database servers and replicating the application server can really balance the load, right? So this is very very good when we are writing things to the system, right? And definitely getting back the response, correct? But what about the read, right? Anyone is hitting to a sort URL, the sort URL has to again go through find the sort URL, and it will get the sort URL from DB and get the sort redirection to the long URL for the user, right? So in this case, what it will happen is the read will be more it will have the high latency. That means it will take much more time to redirect to a particular URL, because getting the long URL for that map to that particular short URL we are trying to access, it takes time, right? So that's why the redirecting to the actual URL also it will take some time, right? So to get rid of that, okay, to make the reading latency little lower, really lower, what we can do, we can make some mechanism or the component available we have in the system design that's called caching, right? The caching is nothing but it is a cache layer. This is cache layer is the in-memory cache layer, which will which will hold some of the data already available in the DB in the cache itself, right? In this cache, what it will do is the frequently accessed URLs, right? URLs can be cached on top in this cache memory, right? Or any kind of algorithm you want to place over here to load the data or store the data or clean the cache, evicting the cache we have data we have uploaded into the cache. So all these things you will definitely get from other previous video, as I keep saying that, right? So we are just using this component, but component internals you can find from the other video, right? So now when you see like this data is available in the cache, now whenever any request hit to the try to hit to the DB, first it will try to hit to the cache, right? The cache service will provide the long URL to the user if that is available in the system, right? If that is not available in the cache, it will always try to go back to the DB and get those. So this is how it can really beneficial to the system caching. What if, let's for example, some of the URLs created from created in United States, and some of the those URLs being read by outside of the United States. Okay, so that comes to the region, right? So when it comes to if we are only storing the data, whatever the URL we have already shortened into the database, and that database is only available in the United States region, then it's always it takes longer time to reach from a different geographical location to the United States region network and to read the URL itself, right? So that will take time, and it's a time taking it's a little time taking, right? So for that, what the other mechanism we can add to the system, data replication, right? The replication, we can replicate this whole database to a different region altogether, right? Maybe a region 1, region 2. So this region might sitting somewhere in the maybe Asian region, and this is sitting in the Western region or some different regions itself, right? So if you have some knowledge around the cloud, so the cloud has the different region concept, right? So that way we can really make the read latency lower and lower while we are reading by replicating the whole data store or whole application server, right? So that's how we can really make more resilient from the reading side of the house as well. What happens whenever we are sending multiple requests, and the servers are not able to really really process those number of requests frequently, right? So for that case, what we can do, we can really add one message queue. What this message queue will do, so even if these servers are not that much performant, or they are not able, that is taking some time to process those data, so the request can be directly stored into the message queue itself, right? So that the service can really read from the message queue and process it whenever they will find the slot, right? So that's how the message queue also come into picture, right? So we have already explained these components in our different bit as well, right? So this way we are not waiting, we are not keep waiting for the for the request be and come to the system and just fail it. Rather, we are just putting that particular request into the queue, and from the subsequent service will pick that particular request from the queue and get it done and send the response, right? So all these things will happen in parallel, right? So in a nutshell, what will be our revised design, right? Yes. So the revised design would be like, here is the user, okay, and it will hit to the service, okay, and the load balancer is sitting here, okay, and then from the load balancer we have set up application servers, application server 1, application server 2, and application server 3. 3, right? So when we are doing this, then the load balancer can hit to any of the system over here, right? So yes, send the request to any of the system. So what we have, we are going to do is we can. So here we had also here, right? So here we put some queue kind of thing, right? So any kind of message queue, right? Any kind of message queue. So from that it will go to that particular service, and it will take care of that. And so we can have another load balancer here, okay? The send the to take care of the storing the service, right? Storing the data into the database, right? So to do so, so maybe we'll have here, as you say, like the database over here. So this can be stored anywhere, right? So now here what we did is, like, while you're trying to store the data, you can directly store the data here, DB, and when it's trying to read the data, it can read the data from the cache layer, right? Cache, okay. So this is read, okay. This is read. This is write, okay, and this is also let's say load or eviction, okay. So that way it can be taken care, right? So this will be load balancer, this is app server, and this is load balancer, this is a database, right? And this is the cache layer, right? So this way we can really manage the whole system when it comes to the scale. There should be a mechanism to access the data, right? So how we are going to access this data, or access their data, or trying to send some request, how it will happen? So it usually happens through APIs, right? So this is another component in our system design landscape, right? So application programming interface, correct? So APIs are really useful for sending the request through the HTTP or HTTPS protocol, right? And it hits to the application server, and the application server will take care of that according to our API we have provided to the user, right, or in the system. So to deal with that this particular use case, the API could be, okay, maybe create sort URL. So what would be the argument for that? It would be the first and foremost is the API sort URL, right? So this will be our arguments to the these are the arguments to the service we have to have, right? So in this case, what is the API key? API key is the key. It's provided by our service, the service we have built. So because we are providing this, we want to block all those anonymous and all those spammers not to screw up our system, right? So that's why whoever has this API key, they can only send the send the request to the system. But if you are opening to the whole world, to the public, then probably this API key sometimes might not make sense, because these are this API key has to have if a user first logs into the system, right? Then only they will get API key for that, right? But long story short, we'll have an API key for our system, and we have to pass our the API should send the long URL as well the short URL. We can have the short URL optional. Why? Because in our system, if you see, like, the user should able to provide the own short URL, right? Own short URL. So user pick its own URL, right? So in that case, if we make it optional, then we can either system can generate the short URL, or user can provide the URL from this. So that's why I'm making it optional, right? So while once it will do all this magic and shorten it and store those details into the database and get the response, then we have to have a call. So we have to have a get API which will get URL. So in that get URL, we need to provide the short URL here. Right? So this short URL, once it will go with the short URL, so it will try to hit the application server, and application server will try to take this short URL and process it, and find this short URL available as a key in the database or in the cache, and return back the long URL, right? It will get that long URL if at all it's available, right? So a long URL, and redirect to the right page. Otherwise, what it will do, it will send like 302 the response. The URL is not available, or it's moved to. And the DB schema design, we already talked about that. DB, what are the things we really need for that? We need user detail. While we are talking about the estimating the data store, so we already talked about like what are the details we are going to store in the database, right? So in this case, so what we are trying to do with user ID, username, and maybe created on, right? So these are the things we are going to use, and for the URL schema, URL the store, right? URL store, what we are going to do, long URL, that's a short URL, first as a key, short URL, and the long URL, and created on, right? Created on. So those are the minimum fields we need in the. You can add the email next to in the user table as well, email, because that will be the email or maybe some credential EWD created on, right? So you can have those fields as well to maintain the user details, right? Database, right? And we already talked about that, how we can replicate the data inside the database and all, right? For the different region and single region as well, right? So these are the minimum requirement we need for the DB to design the store the data into the data. While we are dealing with the database, what should we use as a database? Should we use SQLs or some RDBMS or NO-SQL? NO-SQL, right? So for RDBMS, maybe we can use the Oracle, maybe MySQL, okay, Microsoft DB, all these things, right? So the only thing is like with RDBMS, it's definitely consistent. I mean, it really follows the ACD rule. However, they comes with their own caveats, like number of requests, serving the total number of requests at a time, and the maintainability, and scaling it off and scaling it down, the servers and all, right? So those are the things really need to think of while we are thinking of using RDBMS, right? And when it comes to the NO-SQL is very flexible enough to provide all these benefits. However, NO-SQL also comes with their own caveats, right? So for NO-SQL, it's the biggest problem is like it's an eventual consistency, not the right. It's not consistent right away, right? So it's an eventual consistency, and it runs in a distributed system. There is no guarantee like you are getting only the one record at a time. For the whole whole system, you have to really write your own service to really deal with those duplicates, all those things, right? So because it runs in a distributed system, right? So and it always, whenever you are using this NO-SQL, you always think of the theorem called CAP theorem, okay? CAP theorem. The CAP theorem, we can have a quick session of the CAP theorem, but this is what it is, right? So when NO-SQL comes in picture, we can really use the Mongo, and maybe Cassandra, HBase, Dynamo, and there's a lot of, right? So, but for this use case, probably we are looking for key value stores, right? Key value stores. So the key value stores are definitely we can have all these we can use, but specifically MongoDB is more more related to the document store, right? Cassandra is one of the best way to deal with the this kind of use case. So it stores a key value, and it's already it supports partitions, and also this takes care of the partition hashing and all, right? So that whenever you are configuring the hashing mechanism, so it's already following those criteria, right? So you can deal with that. But when we're talking about all these NO-SQLs, So no-SQLs runs in the distributed system, right? So DynamoDB also, most commonly used for this, key value stores, right? So, but everyone, does, good thing, but the caveats are like eventual consistency, right? So the moment you are writing to the system, the same moment you might not get the data, the same moment the updated data might not reflect at the same time, right? It will be eventually consistent, right? So that's the case. So now the problem is like the uniqueness, right? So we already have one, like it should generate the unique URL, right? So for the unique URL, it has to have maintained somewhere to make it unique, right? But if it's a distributed system, same request might go through multiple servers, right? And in multiple partitions, and that same request might have processed multiple times. When it comes to the multiple times, what it will happen, it will process multiple times, and it will try to multiple sort URLs for the same long URL, right? So that means there are duplicate entries for a specific long URL. There are multiple short URLs. Now customer doesn't know, like user doesn't know, like which short URL to use. So that is most important thing we need to really consider, right? To making it uniqueness. Okay. So for the uniqueness, we can use one thing called UUID, right? So UUID, one of the best thing to use for getting any assigning any unique ID to any specific row. But there is a caveat also. There might possibility there will be a collision, right? So the collision is one of the thing when we are assigning the UUID to the system or to any record to create a short URL. So in some time there might be a case it can generate the same UUID for for that particular record, right? So in this case, but if you go through the wiki, so wiki says like it might you will, when you are using UUID, you might get a collision in 85 years, right? And that's a long duration, but you never know like when you will get, right? So that's how we can use the UID, but that's one of the caveat we have to really think of, like it might overwrite any time in the whole time span. It might overwrite any of the existing URL, right? So that's what we are little bit stepping back to not to use the UID unique system, right? So what would be the alternate for that? Okay, so the alternate for that would be a counter system. So what counter system it would be? So anytime any request comes into the system, so system will generate a unique ID with a counter, right? Counter in the sense like it might generate a UID, but it will add a counter to the system, right? That means the number of requests we are getting to shorten the URL, so there will be that number of that number of unique counter ID will be added to the short URL to generate a short URL, I would say, right? So how that will happen? So what we can do is we can use a mechanism called the tool called zookeeper. There has to be that. So what we can say is we can assign a range of unique numbers, unique counter to every server, right? Every server. That means, let's for example we have 3 servers, right? 3 servers. What we can do is we are estimating we will have 3.7 or 4 billion of requests, right? Or requests to the system, shortening URL. So what we can do is we can divide this particular 3.5 billion, or every day we are going to get somewhere around 1200 URLs per second, right? So what we can do is we can assign for every server, we can assign 10 millions of unique IDs. Unique IDs, right? That's a counter. So what it will do, application server 1 to application server 1 can have 1 to 10 million, and application server 2 will have 10 million plus 1 to 20 million, and the application 3 can have 20 million plus 1 to 30 million, right? Okay, so in this case what will happen is, so whenever any request going through that, so it will try to try to assign one counter for that particular URL and try to store into the database, right? So in this case, so whenever request come into the distributed system, it never know like which server it will go, right? So so in that case what it will happen, so as we have assigned 1 to 10, it's 11 to 20, and it's this is 21 to 30, right? So we have assigned this, but whenever any request comes to the system and it's a distributed system and replicated, any server, it will get the URL. What it will do, it will generate a unique sort URL using counter between 11, 10 million plus 1 to 20 million, any unique number from that. Okay, so it will never ever use below that, below the low level or more than the maximum level, right? So this is how it will get. So every time we are making sure, like whenever we are storing any sort URL, that comes with a unique unique counter. That's why there will be no collision. So now the question is like how it will, how we can make sure like, okay, we are getting the 3.7 million, and but it's just a 30 million counter, right? So whenever any server exhausts its maximum range, then we have to reallocate some more range to that, right? So to do all these things, so the server cannot do their own, because they have, they are running independently, right? So for that we have to have a mechanism, the tool called zookeeper. So this is zookeeper is nothing but a coordinator, right, in a distributed system. So this is a server coordinator. It will have all the detail for the for the server, maybe application server 1, application server 2, application server 3, right? And it will hold the range 0 to 10 million, 10 plus 1 to 20, 20 plus 1 to 30, and so on. So whenever any request come to here, it will go through this counter, okay, this counter. And whenever any number is already used, so it will just, in this zookeeper, the coordinator will apply its own algorithm and keep incrementing the lower range to 2 plus 1 plus 1, right? So that whenever any new request hits to the same server, should not use the use the counter which is already used, right? So those are the things comes into the picture when it comes to the coordination, right? So the server coordination. So this zookeeper will somewhere sitting here to take care of all these servers, right? Servers counter. If zookeeper, probably it will be easier to understand if you heard about high availability, right? High availability is one of the mechanism where we are building the system to make sure like the whole system is highly available, right? So this is what we are talking about, the highly available, right? So highly available in the sense like we have replicated servers, and one server is working as a master and others are working as slave, and if any server goes down, so master should be take care of others and reroute the request to the right server waited, right? So in that case, most of the use cases, the zookeeper is more important to deal with that. This is one of the out of context, but whenever we are really building the high available system, so this zookeeper always comes into picture, okay? And to coordinate the whole system, servers available in the system, and maintaining the workload as well, right? And so that's the story behind that, using the zookeeper, right? So for the minimal latency, we already use the cache for that. to make sure like we have the minimum latency here. And the maintainability, definitely maintainability is easy, because anytime we want to add new server, we can add the new application server over here, and that will be automatically registered in the zookeeper. And this one, I mean, whenever we are trying to add more database server to the system, we can always scale it out, right? So we are just scaling it off. How can we make it scale it down? So definitely there will be other mechanism has to go through, like using some applying some Kubernetes orchestration, or there are some open source orchestration as well to deal with those kind of things to make it scale off and scale down, right? So then we heard about that, and we talk about that. And then some additional features we already talked about, like there should be API for the machine to machine access. So machine to machine access is nothing but when user hits to the system, so user can really request with some arguments or parameters and the specific system. So we can also has to provide some mechanism where the API can really talk one machine to another machine, not specific user to machine, rather machine to machine, right? So there might be a auto-generate machines that use in the organization itself, which really hits to the unique URL. Okay, so basic example. For example, we can say like Twitter, right? When we are sharing any post, so in that case, it will automatically generated a unique short URL behind the scene to share that with a different user, right? So that might be a machine to machine communication, and one machine is hitting to API to the service to get a long URL or something like that, right? And provide the KPI matrix. So that can have another API where we can really deal with finding some analytics. Like, okay, how many number of new KPIs? How many number of new URLs came to the system for the shortening? Okay, for this particular time period, or maybe last 28 days, last 90 days, or last week, right? Or maybe last year, so that we can get a graph out of that, like how the system is performing and how the latency is, and all other operational KPIs as well. So those are the good, APIs that can be built out of those system. So using the API mechanism to build the API to deal with this system, right? Kind of like, okay, get API count by last week, okay, or weekly API count, get weekly stats, for example, stats, right? So what it will do, it will have a maybe get underscore stats is API, and we can say like weekly. So it will give us the detail related to it will group the whole whole number of requests we get into the system, and group by week by week, and get the count over here, right? The counts, how many number of shortening requests we got every week. Maybe we can build another API called get stats region, right? Region. So it will give the stats by region. Okay, region, how many number of requests we got, how many number of requests we got for URL shortening. So those are the things we can get those results. So this kind of start API we can really build for the system, right? So these are the things we can really do. And definitely when we are building a bigger system for the bigger scale, so there are a lot of other factors also come into picture, but definitely this is probably very good. We got very good idea regarding this system, how we are really building if you are going to build a URL shortening system. And I believe this is very much helpful, and thank you so much. Please don't forget to subscribe the channel if you haven't done yet, or click the bell icon as well to get notified the latest uploads or latest videos we have. Have a great one and stay safe. See you in next video. Thank you.